I'm Luc Bourlier. I'm a software engineer at Lightbend, working in the fast data team. So let's get to your first slide. So the name of the talk is a bit of the mouthful, but to start with, I will make sure that we kind of understand part of the title correctly, and we are starting from on the same basis. So, fast data. What do we call fast data? The idea of fast data is to use the tools and algorithms that were created for big data, but using on streaming data, not on data which you have stored somewhere in a distributed data store. And the idea is to get information really fast. The typical way that you get to do fast data is at some point you start to do big data. I mean, you have a product and you have a lot of logs or a lot of information about your product, and you are lucky enough that your boss tells you, okay, we have a lot of data, I want information about the data we get. So you create your big data job, and you run it, and you provide useful information. So your boss says, great, this information was from last week, last year. It would be nice to basically get more up-to-date information. So can you just kind of run the same thing every day? You say, sure, no problem. You tweak a bit your job, and you put it in a cron tab, a nice script and a cron tab, and you run it every day, and you get data every day. And your boss comes back and says, that's really great. Well, the only thing is, I mean, we had a problem, and everybody on Twitter kind of tell us what we had a problem, and we managed it, and the day after we were able to check that, okay, well, now we understand why we had a problem, but it's a day after, it's kind of not so useful. Can you get something faster, like every hour? So he goes, sure. Well, it starts to get a bit more complex because the data you have on 1 hour might not be good enough. You might not have enough data on 1 hour. So you need to basically go over the last 24 hours. And to process the data of the last 24 hours, well, it might take more than 1 hour. So, I mean, you do the work and it's fine. You still can do it with batching. And you provide data up to the hour to your boss. And it still works fine. And then your boss comes back to you and say, it would be nice to basically know right away when we have a problem that we have a problem. Can you do something? And at this point, you get to the fast data. You're processing data as it's coming in, and you're using algorithm of big data to get insight of the data you get. So that's basically how you get to fast data. Reactive applications. So I don't know, was there any reactive application talks so far in Scala days? Okay, there's a few. So who doesn't know about reactive applications still? Cool. I don't have to spend too much time on it. So the part I will mostly look at is on the elastic part, to be able to stay responsive with a different workload, and especially when you have too much data. So I will show you a small demo. The talk was about linking reactive application with fast data. So I have a demo where I have a reactive application, which is doing some computation of pi, just using basic computation with random number and where a dot, a point is landing in an area inside a circle or outside of a circle. And so it's just a reactive application which kind of allow you to see what's the different output you get with different way to manage your random numbers. And I want to add to it a fast data application which is doing statistic analysis of the data which is generated by the reactive application. So let's see that. So to run my test, I'm going to do that on my little small Raspberry Pi cluster, because the fun thing with this guy is there's a few things so we're using Spark also for fast data. And there's a few things that when you start to do a big data, fast data, it's really more fun to do it on a real, or you don't have to do it on real hardware, but at least to a real cluster, because otherwise you may do some mistakes in programming if you're just running on your local machine. So let's see the application in working. So I made a small dashboard, which I need to make bigger. Okay. Yeah, so I have a small dashboard. I can change the number of random number generated per second. I have a view of the values of pi which are computed, which are not that close to pi. So in my fast forced by my Spark application, my fast data application, I see the number of elements I receive every second, and the time it takes to process the data which I received every second. I will explain just after how Spark and Spark Streaming is working, so it will make a bit more sense after. So what I can do is I can start to increase the rate of number of elements I generate. So increase the number. So the whole thing is, this is the Reactive application is created using Reactive Streams. So everything is managed with batch pressures. So if part of the Reactive application is started to get too slow, then random number generator will start to not push as many elements as I ask him to do. So it's slow. If the hardware is not fast enough, which is Raspberry Pi, so it's not very fast. So if the hardware is not fast enough to manage all the data I produce, the rate of generation of numbers will slow down. So when I go for 1,000 elements, it's still going fine. So this is the requested rate, and this is the actual rate, which I check. So everything is going fine. And Spark is getting about 3,000 records, and it takes half a second to process the data which is received in 1 second. So we are fine. So let's double that and see what we get. So the application updates, and my number generator kind of fluctuates sometimes, so it's not totally always at 2,000, but it's close to it. And my value of pi is getting better, which is cool. Spark is still going fine, getting a fair amount of records, and the execution time is still a bit out under 1 second per second. So I'm still going fine. So let's double that again. And okay, let me check what code am I running. I think I'm running the wrong code. Let's try again. Oh yeah, that's the wrong one. It's okay. You can just restart it. Hello? All right, it's time for Spark to start. There we go. We are live. So yeah, so why I'm pushing so many elements? Okay, we are pushing about, so we are getting a bit to the limit of the machine, so it's kind of hard to get the exact value. So I'm pushing 4,000 elements per second, and if I look at my execution time, I'm spending more than 1 second every second to compute my data. And this number here, which was at 0 before, now is growing and growing. If you look at Spark itself, and I'm refreshing the statistic of the job I'm running, so I see that basically every time I'm doing something, I'm adding some scheduling delay, which means that every second, when I want to try to compute the values for the result for the values that arrive in a second, it takes more and more time to even start to do the computation. So let's see if I refresh. So yeah, so now I'm delayed by 3 seconds. So the result I'm getting out of my Spark applications are not for the data which I receive right now, it's for the data that I received 3 seconds ago. And all the data which has been received since now and 20 seconds ago, which is not processed yet, is stored in memory. So I really have a problem. I mean, the information I get is from old data. The new data is getting stored, and if I don't kill this application really fast, Spark won't really crash, because Spark is really resilient and doesn't really crash. It will just not process data anymore. And basically, it's not useful for you. Spark is fine, it won't crash, but your application is not working. So let's see what we can do about that. I'm gonna just kill that and restart for the next demo. Oops, where is my mouse? Okay, let's get back to the slides. So let's go a bit inside Spark and Spark streaming. So Spark is basically an evolution of the MapReduce model, which is used in Hadoop. The big changes between Hadoop and Spark is Spark tried to get all the computation to be done in memory. In Hadoop, if you know the MapReduce model, the data basically after each cycle, the data is written back to disk. So it might be fine for big amount of data and some type of data, but if you want to do operation of machine learning that need to do a lot of repetition of cycles, every time, if you do it in Hadoop, you read the data, you transform it, and you write it back to disk, and you read it again and again and again. So that's really slow. So Spark does most of the operation in memory, which allow you to cut down the part about saving data on disk, which is slow. And also, since Spark 1.4, I think, and later, there has been a lot of optimization that has been done to a lot of work that has been done in Spark to optimize the computation. So in Spark, you describe what you want to do on the data, and now with the latest versions, it takes this description and compile it in a way which is really fast to execute. So Spark, the basic Spark, is working on batch of data. You just give it a big amount of data and a lot of machines, or a small amount of data and a few machines, and you tell it, please compute that. On top of that, Spark streaming has been created. So the idea of Spark streaming is to reuse all the infrastructure of Spark, but for streaming data. And the way it has been done is to process data as mini batch. So before I was speaking about 1 second, the time to process data received in 1 second, in less or more than 1 second. It's because my Spark streaming job is configured in such a way that it does mini batch of 1 second. And so during 1 second, well, each second it receives the data, store it internally, and then it's every second it tries to launch a job, normal Spark job, to process this data. So yeah, so that it is. And then normally, if everything goes well, every second about, in my specific case, you get a result for your streaming data. So a lot of work has been done over the years in Spark to make sure that you can resist to a lot of failures. So hardware and software and network and all the things. And specifically for Spark streaming, there's a lot of effort has been done to make sure that even if something fails, you never lose data, and you can get a guarantee of at least once processing of all your data. And since a few version, there's support to manage excess volume of data, which is exactly what we had. Spark was starting to get too much data to process and was not able to process it fast enough. Which leads us to back pressure. So back pressure is exactly that. The idea of back pressure is for a slow consumer to be able to tell to a producer, to a fast producer, that this is too much data, I cannot process that much, and this is how much I can process. A classic example of back pressure is TCP. If you look, I don't know which level of stack of TCP. I think it might be, yeah, it's TCP. So it's it's in the TCP protocol itself. If you look at the TCP protocol itself, there's always information on all the trams that are going between both sides of the TCP connection. There's information about, okay, this is how much buffer size I still have. And basically each part of your TCP connection, all the routers and things like that, they all speak to each other saying that, okay, this is how much space I have available in my buffer. And you might not have ever seen it because you may not ever had to do performance tests on that. But if you do it in Java and you send a lot of data, and on the other side, the thing is not reading or not reading fast enough, at some point you're going to get an exception of, I don't remember exactly what the exception is, but it's basically telling you that, yeah, all the buffers are full, I cannot write in it anymore. So it is a kind of back pressure at the TCP level. Yes. So back pressure. So the idea of back pressure has been added to Spark. Before Spark 1.4, I won't go too deep on this slide. There was no real good way to manage the amount of data that was received in Spark streaming. You could set the max rate, which you had to guess somehow, which was totally static. So if you added more nodes on your cluster, it didn't change. So it was not great. In Spark 1.5, my team, my live band, we worked on adding back pressure in Spark. And the basic way it works is so we have the mini batch, and at the end of each mini batch, we look at how many messages we received, were processed, how long it took to process the messages, and from this data, compute an estimate of the upper bound of how many entries in the mini batch can be processed in 1 second. And this information is sent to the receivers to be able to be sent up the stream as needed. Yes. Yes, so what I said. So at the end of each batch, you get information about how it went and how many elements was processed and how long it took, the time it took to process it, and also the scheduling delay. So if for some whatever reason you had some delay before, you also know about that. Sorry. And so the way the rate is computed is really mostly like, okay, the number of elements divided by the time you process multiplied by the time the length the length of your mini batch time. So it just gives you a straight linear numbers. Except that just doing that is not enough, because as I said before, you might have some delay that had been accumulated over time, which can come from whatever. I mean, for whatever reason, your machine has been slowed down because some other operation has been running at the same time or something like that. So something changed, and you did accumulate some delay. So the way it exactly works, it's using a proportional integrative derivative algorithm. This is totally not new and has not been created for Spark at all. I'm not sure if it has been created for, but it was used a lot, or it is still used at first to be able to pilot big ships. So if you take a cargo ship, a huge cargo ship, maybe a cruise ship also, when you start to turn the wheel at the helm, at some point the ship will turn. But if you stop trying to turn the ship when you see the ship starting to turn, it's too late, because you will overshoot. So the idea of the PID is to have all the characteristics of the system in it, so you can send information to, in the case of the ship, to the helm, to say, okay, how much you need to turn and when you need to stop turning. And in Spark, it's used to send as back pressure information exactly the amount of data you can process, and also the amount of data you can process at this specific time to be able to recover from the scheduling delay. Yeah, so those are the details of those are details of how you configure back pressure system in Spark. I mean, it would be interesting if you want to look at the slide later, but I will go through in the code exactly. So this is an image of the test I created when we did the implementation of the system. So what you see is the same test running twice on a system which with back pressure enabled, and also one which doesn't have back pressure enabled. And the red bars are the scheduling delay. So you see that, yeah. So in the first case, we create a lot of scheduling delay, and also the blue line is the memory available to the system. So the memory is going down. At some point, going to get to 0, and your system will be really unhappy, and your information is getting really, the information you get out of the system is getting really delayed. And when we enable back pressure, so we do have a bit of scheduling delay which appears. It's mainly due because if you get close to the limit of how many elements you can process, you might overshoot a little bit. So there's a bit of scheduling delay which appears, but the algorithm, the PID system, manage the fact that you have a scheduling delay and reduce a bit the number of elements it accepts, and to resolve the scheduling delay. Yeah, so back pressure in Spark 1.5 and the version after that is working fairly well. I got feedback from one of my former colleagues who is working now in the industry that they like it and they will use it a lot, and they may need to have we might need to work to improve it a little bit, because they saw that basically managing record by record is a bit slow, and now they do aggregate of data in one record, which means that each record might not be exactly the same size, so it's a bit of a problem. But in general case, it's working very well. And yeah, so we have a reactive application written in Stream, which is doing everything fine, and Stream, sorry. And Stream has a back pressure built-in, so there's no problem on this side. And we have Spark, which support back pressure and give information to the receiver, so the part which receives the data, the information about how much it can handle every second. And we need to connect the two things. So the thing we use to connect everything together is Reactive Streams. Reactive Stream is a small set of interfaces, Java interfaces, which have been created just for this purpose. The whole purpose of Reactive Stream is to be able to connect two systems which have back pressure information, so they can communicate to each other. It's really a pure interface to connect libraries and systems. So right now, if you want to use it, you can go to reactivestream.org and get all the information. And those interfaces are going to be included in Java 9 in the concurrent package, so as soon as Java 9 is released. With a little thing that, well, the package name won't be exactly the same, so you might need to change a bit your code when we move to Java 9. But I mean, so Reactive Stream is very good. I mean, it has been accepted and will be in Java 9. So yeah, so I can show you again the same thing, the same demo. So the difference between the first one and this one is in this one I did enable back pressure in Spark, which will be the same thing if I just basically make the connection with Reactive Stream. And let's see what we get. So let's refresh this guy. So it was running on the back. Oh, okay. Well, it was running fine, in fact. I forgot to change the parameter of the application, so it was running full speed all the time already. And it didn't die, which is a good thing. So I asked the system I forgot to reset, so it was still asking for 4,000 elements per second, and it is producing way less. And the reason it is producing way less is, wait. Okay, yeah, so yeah, the reply has a problem that, yeah, it doesn't get unstable. It gets hard to know exactly the performance of the system when you start to push it really hard. So those numbers are moving very high. But the good thing is, if you look at the graphs, so the execution time is staying around 1 second, which is what we aim for. And there is some scheduling delay which is getting introduced in the system because it is working too hard, and it is really hard to get to the flat value. If I run it on my machine, well, no, if I run it the same test on EC2 machine of normal size, it is way more stable. But the fact is, we don't have real scheduling delay doesn't accumulate. It gets there, but it gets fixed, and the processing time is flat. So our system won't crash, which is what we wanted to get to. So one additional thing, yeah, I don't have much the slides. Okay, I know what I want to do. One additional thing I wanted to say let's get back to the drawing of the system. So the way I manage the fact that Spark is telling me that it cannot handle all the data I have is basically the back pressure information is going all the way back to the random number generator, and the random number generator basically drops elements. If it tried to push more data to the system and sees that it cannot, so it just drop elements, which is really a crude way to implement that. It works. So in a real case, the way you will do it is there's multiple ways. If you basically the data you process are logs. In your logs, you might have some info, some warnings, and some errors. And if you see you cannot send all the data fast enough to the system, you might start to drop info data because the warnings or errors are likely what you care much about. Otherwise, another solution, which I cannot do on this thing because I'm limited, I limited myself to only 5 Raspberry Pis, is you could just decide to just add an extra node to Spark. On your system, that does real computation, adding an extra node will make the computation faster. So you can just detect the fact that you cannot push data. Spark cannot process data fast enough in your application, not in Spark. So in your application, you detect that something is too slow in the system, and you can just scale your system up and produce more data to be able to process more data. Okay. Well, thanks everybody.